China is quietly researching a civil jet designed to do something no passenger aircraft has been allowed to do for decades. Fly faster than sound over land. Not by changing the rules, but by trying to work around the very problem that shuts supersonic travel down in the first place. That problem ended Concorde. And if this attempt fails, Concorde may remain the last supersonic passenger aircraft the world ever sees. The aircraft is known as the C949. But before you picture a finished jet, there's something important to understand. This is not a finished aircraft. It is a long-running research effort. It exists to answer one question the West largely walked away from. Does supersonic flight have to be banned forever, or can the aircraft itself change enough to make that ban negotiable? To answer that, we have to go back to why supersonic passenger flight was stopped in the first place and why that decision has survived every advance since. When Concorde was retired in 2003, it did not fail in the way most people assume. The aircraft did not age out, it did not become unsafe, and it did not fall behind technologically. In fact, by the end of its service life, Concorde was still doing something no other passenger aircraft has managed since. It was moving people faster than the speed of sound, reliably, on a fixed schedule, across the Atlantic. What ultimately ended Concorde was not engineering. It was tolerance. The fatal Air France Flight 4590 crash in 2000 didn't invalidate the aircraft's design, but it accelerated public, political, and commercial intolerance toward an already controversial program. When an aircraft crosses the speed of sound, pressure builds and collapses into a shockwave that reaches the ground as a loud boom. That sound was never just an annoyance. Overpopulated areas, it became a political liability. During Concorde's early years, residents beneath test corridors reported rattling windows, cracked plaster, and constant disturbances. Governments quickly realized that allowing routine supersonic flight over land would mean accepting public backlash at scale. The response was decisive. The United States banned supersonic flight over land in the early 1970s. European regulators followed similar logic. Other countries aligned quietly. By the time Concorde entered regular service, the rules were already set. Supersonic flight was restricted to ocean crossings, where noise complaints could not reach voters. This single limitation defined Concorde's fate. Airlines could only operate a narrow set of routes. Expansion into continental markets was impossible. The aircraft became dependent on a small group of premium passengers willing to pay extreme prices for time savings. Operating costs remained high, fuel efficiency remained poor, and there was no political appetite to revisit the rules. By the early 2000s, the lesson was clear. Supersonic passenger flight was technically achievable, but socially unacceptable. Western aerospace firms reached the same conclusion independently. Faster aircraft were no longer worth the regulatory risk. Research funding dried up. Civil supersonic transport became a closed chapter, not because the world forgot how to build it, but because no one could see a way around the noise. 4 years after Concorde, supersonic passenger flight was treated as a closed case. Not because engineers ran out of ideas, but because governments ran out of patience. The noise problem had no acceptable solution, and without political backing, there was no reason to keep pushing. The breakthrough did not come from new aircraft, but from better modeling. Advances in computational fluid dynamics allowed engineers to simulate airflow and shockwaves with far greater precision than was possible during Concorde's era. For the first time, researchers could study not just how a sonic boom formed, but how multiple shockwaves interacted along the length of an aircraft. This led to a critical realization. If those shockwaves could be shaped in space correctly, the pressure reaching the ground could be reduced. Not removed, but softened enough to change how it was perceived. The question shifted from how to fly faster to how to manage pressure. Much of this work gained visibility through research led by NASA, particularly its quiet supersonic studies. Wind tunnel testing and simulations showed that long, carefully sculpted aircraft shapes could redistribute pressure over time. Instead of a sharp crack, the sound could arrive as a series of lower-intensity pulses. The goal was never silence. The goal was tolerance. These programs were not aimed at launching an airliner. They were about proving that the sonic boom was a design variable. That insight did not stay confined to Western research institutions. Chinese aerospace universities began publishing similar studies, referencing the same low boom principles. Curved fuselage shaping, pressure redistribution, and trade-offs between speed, range, and noise. At first, this work appeared academic. Over time, it became more coordinated. Rather than chasing maximum speed, Chinese researchers focused on survivability within future regulations. Lower cruise speed, longer range, and smaller passenger counts. The emphasis was not on beating Concorde, but on avoiding its fate. By the time the C949 concept appeared in public reporting, it was clear this was not a sudden idea. It was a result of years of quiet groundwork, built on the belief that the supersonic ban might not be permanent if the aircraft itself changed first. By the time the name C949 began circulating outside academic circles, confusion followed quickly. Online posts and headlines started describing it as a coming aircraft, sometimes even suggesting a future rollout. That framing is misleading. The C949 is not an aircraft program in the conventional sense. It exists as a reference design, used to test trade-offs long before any commitment to build. This distinction matters. The C949 sits in the same category as many long-range aerospace research concepts. Speed versus noise, range versus efficiency, complexity versus risk. Its value lies in what it teaches engineers, not in how close it is to entering service. That said, the concept is not vague. Research papers consistently point to a cruise speed around Mach 1.6. This is slower than Concorde, but intentional. Higher speeds produce stronger shockwaves and higher thermal loads. By backing off slightly, designers gain more control over pressure shaping and fuel consumption. The aircraft is also designed for long-range flight, comparable to intercontinental subsonic routes. Passenger capacity is limited, typically described as a few dozen seats in a premium layout. This is not mass transport. It is a niche aircraft aimed at government, business, and strategic travel. Every one of these choices reflects lessons learned from Concorde. Concorde chased maximum speed and accepted the consequences. The C949 concept does the opposite. It prioritizes regulatory survival over spectacle. Smaller fleet size reduces certification exposure. Lower passenger counts reduce political scrutiny. And long timelines allow technology to mature without public pressure. This is why the absence of a launch date is not a weakness. It is part of the strategy. The C949 is best understood as a testbed on paper, a way for China to build competence in areas Western aerospace largely paused. Whether the aircraft ever flies is still an open question, but the research itself is already doing its job. At the center of the C949 concept is a simple but difficult idea. If the sonic boom is what triggers bans and backlash, then the aircraft must be shaped to control how that boom forms in the first place. When an aircraft crosses the speed of sound, pressure waves build up along its nose, wings, and tail. In conventional designs, those waves merge into a single strong shock that travels downward. That collapse is what produces the familiar explosive sound on the ground. The C949 design proposes spreading that process out. Instead of allowing shockwaves to stack and merge, the fuselage is shaped to stretch them along the length of the aircraft. A long curved body changes how pressure rises and falls as the aircraft moves forward. In theory, this prevents the formation of a sharp pressure spike and replaces it with several smaller ones. The goal is not silence. It is reduction. On paper, this approach can lower peak overpressure to levels closer to distant thunder than a sudden crack. That distinction matters. Regulators care less about whether a sound exists, and more about whether it causes disruption or damage. This concept is supported by wind tunnel testing and computer simulations. Similar shaping principles are being explored elsewhere, including in experimental aircraft programs. But there is a critical limitation that cannot be ignored. The challenge is scale. What works in simulations and wind tunnels has not yet been proven reliable across full-size aircraft, changing weather, and real-world operations. Regulators would demand consistency, not one successful pass. The C949 concept assumes that low-boom shaping can be made reliable enough to support routine operations over land. That assumption remains unproven. It is a design goal, not a demonstrated outcome, which means the aircraft's future does not hinge only on engineering success. It hinges on whether reduced noise is considered acceptable noise, and that decision will not be made in a wind tunnel. Supersonic flight does not just make aircraft faster, it makes them less forgiving. As speed increases, the relationship between lift, drag, and balance becomes far more sensitive. Small changes in weight or control surface position can have outsized effects. What feels stable at subsonic speeds can become unstable very quickly once shockwaves begin interacting with the airframe. This was one of Concorde's constant challenges. To stay balanced, Concorde relied on fuel as ballast, actively pumping it between tanks during flight to control the aircraft's center of gravity. The system worked, but it added complexity and workload. Pilots were managing performance at the edge of what was comfortable every single flight. The C949 concept builds directly on that lesson. Instead of manual intervention, research outlines an automated system that continuously adjusts both control surfaces and fuel distribution. Fuel is not just burned. It is moved deliberately to keep the aircraft within narrow stability limits across different speed regimes. This is where advanced flight control logic becomes critical. The difference here is how tight the tolerances are. At supersonic cruise, stability margins shrink. There is far less room for delayed response or unexpected behavior. The proposed system integrates real-time monitoring of center of gravity, aerodynamic loads, and trim requirements. The goal is to minimize drag while maintaining control authority, even as fuel shifts and external conditions change. This approach is evolutionary, not revolutionary. The technology exists in pieces today. What is new is the environment it would operate in. Supersonic flight magnifies every era. A control law that works perfectly at one speed may behave very differently at another. Automated systems must handle transitions smoothly, without pilot intervention, and without introducing oscillations or instability. This is why flight control is not a secondary feature in the C949 concept. It is foundational. Without precise control, low boom shaping loses effectiveness. Fuel efficiency drops. Safety margins shrink. The aircraft's success would depend on software behaving flawlessly in conditions where there is little time to recover from mistakes. Which brings the design back to its most unforgiving truth. At supersonic speeds, technology does not just enable performance. It replaces tolerance. No matter how advanced the aerodynamics or flight controls become, one problem sits above all others. The C949 has no engine. This is not an oversight. It is a reflection of how difficult the problem really is. A civil supersonic airliner needs an engine that can operate efficiently across a wide range of speeds, meet strict noise limits, survive extreme thermal loads, and still achieve acceptable range. Concorde solved this with afterburning turbojets, but at the cost of fuel efficiency and noise. That approach is no longer viable. Modern concepts point toward variable cycle engines, which can behave differently at subsonic and supersonic speeds. In theory, this allows better efficiency and lower noise. In practice, such engines remain complex, heavy, and largely unproven in civil service. Even if a suitable engine were developed, certification would remain a major hurdle. Civil standards demand reliability over thousands of hours, not experimental success. These constraints are not unique to China. They apply to anyone attempting this problem. And even if an engine was solved, overland supersonic flight bans remain in place across most of the world. Changing them would require convincing regulators that reduced noise is consistently acceptable, not just occasionally impressive. That decision ultimately flows through bodies like International Civil Aviation Organization, where consensus moves slowly and cautiously. Regulators do not certify intentions. They certify outcomes. This is why the C949 concept avoids near-term promises. China is not betting that rules will suddenly change. It is positioning itself to be ready if they do. By developing design knowledge, control systems, and aerodynamic models now, it gains leverage later. If the ban never moves, the aircraft may never fly. But if the ban softens even slightly, the country that prepared early will shape how that change happens. That is the real strategic value of the C949. Not speed alone, but readiness. Even if the technology works, and even if the rules change, should supersonic passenger flight return at all, there is a real possibility that the C949 never leaves the page. No prototype, no test flights, no supersonic return to commercial service. And that outcome would not mean the effort failed. In aerospace, research programs often matter more for what they produce indirectly than for the vehicles they create. The C949 concept feeds directly into areas China already considers strategic priorities. Advanced computational aerodynamics, high-speed flight control logic, fuel management at extreme conditions. These are not niche skills. They apply to military aviation, long-range strike platforms, and hypersonic research. Even without a flying aircraft, the data generated through this work improves China's ability to design complex airframes. It trains engineers. It strengthens simulation models. And it shortens future development cycles in adjacent programs. Many Western aerospace breakthroughs originated in projects that never entered service. Their value was not in production numbers, but in capability transfer. If the C949 remains a research pathway, it still succeeds in building knowledge the country did not previously have. That alone justifies the investment. If the C949 or a successor does eventually fly, the consequences extend well beyond China. It would mark the first non-Western supersonic civil aircraft program to reach operational reality. That matters symbolically. For decades, leadership in civil aviation design has been dominated by the United States and Europe. Supersonic flight was a Western achievement, and its abandonment was a Western decision. A successful Chinese program would break that pattern. It would also force regulators to confront a problem they have avoided for years. If an aircraft can demonstrate consistently reduced noise over land, blanket bans become harder to defend. Not because the noise disappears, but because its impact changes. That does not guarantee approval, but it does reopen debate. Airlines, governments, and manufacturers would all be pulled into discussions they have sidelined since Concorde. Route planning, environmental trade-offs, public tolerance, economic justification. None of these questions have been settled. They have simply been postponed. A flying aircraft brings them back. Supersonic aircraft consume more fuel per passenger. They concentrate benefits among a small group of travelers. They challenge climate goals that push aviation in the opposite direction. Faster travel saves time, but it does not serve mass mobility. The C949 does not pretend otherwise. It is designed for elite travel, not public transport. That honesty is part of its realism, but it also limits its appeal. China's supersonic jet is not a promise. It is a test of whether technology can change policy, or whether the limits were never technical to begin with. Whether supersonic passenger flight should return is no longer a technical question alone. It is a political and societal one. The real question is whether the world would allow it. And if that debate reopens, the country that prepared first will shape how it ends.